So let's review electromagnetic radiation, right? Topics that you've touched on in general chemistry and physics. And so when we think about magnetic radiation, we think about light, and we think about light being a wave, right? So wave looks something like this, and there's different parts of these waves that describe their properties. One is the distance from peak to peak or from trough to trough. This is what's known as the wavelength. And the wavelength determines, we're going to say what color in these quotations of light it is, right? So it doesn't have to be a color. It can be, right? Some wavelengths are red, some are purple, some are blue, but some are out of our visible range, but they're just a different wavelength of light. So instead of saying color, you could say the type of light, or if it's maybe an X-ray, or maybe it's a radio wave, or a microwave, or an infrared ray, or a gamma ray, all kinds of things. They're just light at different wavelengths. So there's that component. And then the other component is kind of half the height of this. This is called the amplitude. And this is related to the brightness of the light. Right. So the wavelength determines the color or the type of light, and then the amplitude determines how bright that light is. So for example, we could have a wave like this, or we could have a wave like this, right? We can see that this wave has a big wavelength, whereas this wave has a much smaller wavelength. And we say that these big wavelength ones are low energy light, and these small wavelength ones are high energy light. So one way we can describe the property of light is to talk about its wavelength. Another way to describe light that's often talked about is the frequency, which gets this kind of Roman V symbol. And frequency is just kind of the inverse of wavelength. Frequency is the number of waves that pass a point over a period of time. So if the wavelength is really small, you're going to have a bunch of waves pass a point in a small amount of time. If the wavelength is really long, you're going to have less waves pass over. And the equation to relate frequency and wavelength is that frequency is equal to c over lambda, where this V is frequency. This c is the speed of light, so it's just a constant. And then this lambda is the wavelength. And so you can see they're inversely proportional, that is frequency and wavelength, right? So when we have this big wavelength, we have a low frequency. And then when we have this small wavelength, we have a high frequency. And you can see how that correlates with energy too. High frequency is higher energy, low frequency is lower energy. And you can relate the energy as an equation as well. We can say E is equal to H, which is just a constant, times the frequency, or we could replace this with wavelength, right? Don't worry about the H, don't worry about the constant. We're not really going to be doing any math. This is really just background knowledge. And then here's just a little picture that demonstrates the different types of light. You can see in this kind of narrow defined section, that's what we define as visible light. And there's nothing exceptionally special about visible light. It's just that we have sensors that allow us to pick up this light. But there's constantly rays going around us, and they're just different wavelengths of electromagnetic radiation. On the really long side, you have something like radio waves, and you can see these are about 10 to the third meter, so about 1,000 meters. So that's the size of like a building. So you can see they can be really, really large. Or on the other side, you have gamma rays, which are very, very, very tiny. So you can see you have a wide range. We'll be focusing on this infrared light for our spectroscopy.